Imagine a spacecraft so powerful it could dwarf every rocket we've ever built. A machine so revolutionary it could have turned science fiction into reality 60 years ago. Now, imagine that we actually built it, tested it, and proved it worked. And then imagine we threw it all away. In the late 1950s, American scientists designed a spacecraft propelled by nuclear explosions. Not nuclear reactors, actual atomic weapons, detonating one after another beneath a massive steel plate, propelling a vehicle skyward on waves of thermonuclear energy. This wasn't a fantasy sketched in the margins of a pulp magazine. This was Project Orion, and the physics were sound. The engineering was real, the potential was staggering. A spacecraft that could carry payloads to orbit that made the mighty Saturn V look like a toy. A vehicle that could revolutionize space exploration and unlock the solar system in ways we still can't achieve today, 70 years later. But Project Orion died, killed by the very nuclear forces it sought to harness, and humanity has been crawling through space ever since, using technology that the Orion team would have considered hopelessly primitive. This is the story of the most audacious spacecraft ever designed and why we abandoned our best chance at the stars. The idea was born in the aftermath of World War II, when the atom's terrible power was still fresh in everyone's minds. Nuclear weapons had ended the war, but they had also opened a Pandora's box of possibilities. What if that same explosive force, the most concentrated energy source humanity had ever created, could be used not for destruction, but for creation? What if you could ride atomic bombs to space? The concept sounds insane. It is insane, but it's also brilliant. Here's how it works. Imagine a massive spacecraft with a thick steel plate at its base, the pusher plate. You drop a nuclear bomb behind the ship, detonate it, and the explosion hits the pusher plate with a shockwave of unimaginable force. But instead of vaporizing the ship, the energy is absorbed by a system of enormous shock absorbers. Think hydraulic pistons the size of tree trunks that compress and smooth out the acceleration. Then you do it again, and again. One bomb every few seconds, each one driving the ship faster and faster until you're screaming through space at velocities chemical rockets can only dream of. The physics were surprisingly straightforward. Nuclear weapons release energy in a very specific way. A pulse of electromagnetic radiation, followed by a blast wave of superheated plasma. If you could capture even a fraction of that energy and convert it into thrust, you'd have a propulsion system orders of magnitude more powerful than anything chemistry could provide. Chemical rockets are limited by the energy stored in molecular bonds. Nuclear bombs tap into the energy stored in atomic nuclei, millions of times more concentrated. But understanding the physics and building the hardware are two very different challenges. That's where Ted Taylor entered the picture. Taylor was a weapons designer from Los Alamos, one of the brilliant minds who had helped create America's nuclear arsenal. He'd designed some of the most efficient nuclear bombs ever built, small, portable, elegant in their terrible power. But Taylor was also a dreamer, and he'd become captivated by an idea. What if his bombs could open the cosmos instead of destroying cities? In the mid-1950s, Taylor began working on what would become Project Orion at General Atomics in San Diego. The concept had been floating around in various forms, but Taylor brought weapons expertise and an almost obsessive attention to detail. He understood nuclear devices better than almost anyone alive, and he could see how to optimize them, not for maximum destruction, but for maximum thrust. Small, clean bombs that would pulse regularly, pushing a spacecraft to incredible velocities. Then, in 1958, Freeman Dyson joined the team. Dyson was already a legendary theoretical physicist, a man who thought in terms of cosmic timescales and interstellar distances. Where Taylor brought practical weapons knowledge, Dyson brought visionary ambition and mathematical rigor. Together, they began to calculate what Orion could actually achieve, and the numbers were intoxicating. The performance gap between Orion and conventional rockets wasn't incremental, it was revolutionary. Chemical rockets operate with what's called specific impulse, a measure of efficiency. The best chemical engines achieve around 450 seconds of specific impulse. Orion's nuclear pulse propulsion would achieve 6,000 to 10,000 seconds. That's not twice as good. That's not even 10 times as good. That's a fundamental leap to an entirely different class of propulsion, like comparing a Formula One race car to a horse-drawn wagon, then multiplying that difference again. What did those numbers mean in practice? They meant payload capacities that seem impossible even today. The Saturn V rocket that took humanity to the moon could lift about 140 tons to low Earth orbit, an achievement that required one of the largest machines ever built. The baseline Orion design, a 4,000-ton spacecraft, could lift 1,000 tons to orbit in a single launch from Earth's surface. No multi-stage rockets, no orbital assembly, just a massive ship riding a controlled series of nuclear detonations straight up into space. But before they could convince anyone to fund a full-scale Orion, they needed proof. They needed to demonstrate that the basic concept, riding sequential explosions without being torn apart, actually worked. So in 1959, at Point Loma near San Diego, they built a test vehicle. They called it Hot Rod. Hot Rod was a scale model, a metal cylinder about a meter tall with a small pusher plate at its base. Obviously, they couldn't use actual nuclear weapons for the test, so they used conventional high explosives, C4 charges arranged to detonate in rapid sequence. The test was simple in concept, but terrifying in execution. 6 charges would explode one after another beneath the vehicle, and they'd see if it could ride the shockwaves upward without being destroyed. The team gathered at the test site in August 1959. Careers were on the line. If Hot Rod failed, if it tumbled or shattered or simply didn't work, Project Orion might die before it truly began. They triggered the sequence. The first charge detonated with a sharp crack, and Hot Rod lurched upward, then the second, then the third. Each explosion propelled the vehicle higher, the pusher plate absorbing the shock, the whole assembly staying stable. 6 explosions in rapid succession, and Hot Rod climbed to about 100 feet before descending and landing intact. It worked. The basic physics were sound. You could ride controlled explosions. The team was euphoric. The key was in the details. The pusher plate wasn't just bare metal. It was coated with a layer of graphite grease. With each explosion, a thin layer of this coating would ablate away, vaporizing and carrying away the intense heat. This protected the underlying metal from being eroded or melted. The shock absorbers, even in this small model, compressed and extended with each blast, smoothing out the acceleration pulses into something a spacecraft structure and eventually a human crew could survive. With proof of concept in hand, the team began designing the real thing. And the real thing was magnificent. The baseline Orion was enormous, larger than a naval destroyer. The pusher plate alone would be over 40 feet in diameter, made of steel thick enough to absorb nuclear shock waves. Above it, the massive shock absorber system, pistons as thick as tree trunks, filled with hydraulic fluid, designed to compress under each nuclear pulse and then extend, ready for the next blast. Higher up, the crew compartment, shielded and isolated from the violence below. And throughout the ship, a magazine containing hundreds of nuclear bombs, each one a carefully designed device yielding about 0.15 kilotons, roughly 1/100th the power of the Hiroshima bomb. The launch sequence they envisioned was like nothing ever attempted. The spacecraft would sit on the launch pad, fully fueled and loaded. At ignition, bombs would be ejected through a hole in the center of the pusher plate, falling behind the ship. They'd detonate at a precise distance, maybe 200 feet back, and the explosion would hit the pusher plate as an expanding sphere of plasma. The shock absorbers would compress, absorbing the brutal acceleration spike and converting it into a smoother push. 1 second later, another bomb, another explosion, another push. The ship would rise on a pillar of nuclear fire, accelerating upward at 2 to 4 Gs, uncomfortable for the crew, but survivable. Within minutes, Orion would be in orbit. Within hours, it could be on its way to the moon. Within weeks, it could reach Mars. The mission profiles Dyson and Taylor calculated seemed like pure fantasy, but the math was solid. A Mars expedition carrying a crew of 20 with enough supplies for a year-long surface stay, launched in a single vehicle, arriving in 4 weeks instead of the 6 to 9 months required by chemical rockets. An expedition to Jupiter's moons, carrying tons of scientific equipment, able to land on those distant worlds using the same nuclear pulse system, and then return to Earth. They even sketched out missions to Saturn, Uranus, Neptune, a grand tour of the outer solar system that could be accomplished in less than a decade by a single Orion spacecraft. The most audacious proposal was an interstellar mission, a massive Orion powered by thermonuclear bombs. Not fission devices, but fusion weapons with far greater yields, could theoretically accelerate to several % of the speed of light. A voyage to Alpha Centauri, the nearest star system, could be completed within a human lifetime, not in some distant future when we've mastered exotic physics, but with 1960s technology and enough political will to build it. The economics, surprisingly, favored Orion. Yes, the upfront cost would be enormous, billions of dollars to develop and build. But the payload capacity was so vast that the cost per kilogram to orbit would actually be cheaper than chemical rockets. And unlike conventional spacecraft that required multiple launches and complex orbital assembly, Orion could do everything in one shot: launch from Earth, travel to the destination, land if needed, and return home. It was reusable in a way that made the space shuttle look like a disposable toy. The crew experience would be strange but manageable. Despite riding nuclear explosions, the shock absorber system would limit the acceleration to 2 to 4 Gs, about what fighter pilots experience in tight turns. The ride would be rough, certainly. Imagine sitting in a vehicle that's being kicked by a giant's foot once every second, each kick a bit harder than the last. But humans can tolerate that. Astronauts have endured worse during rocket launches and re-entries. For a brief moment in the late 1950s and early 1960s, it seemed possible. The technology worked, the designs were solid, the military was interested. Orion could deliver massive payloads anywhere in the solar system, which had obvious strategic implications. NASA was intrigued by the possibilities for deep space exploration. Freeman Dyson was calculating trajectories and writing papers, convinced that Orion represented humanity's destiny among the stars. But there was a problem. Actually, there were several problems, and they were getting harder to ignore. Freeman Dyson, the visionary theorist, was also a careful mathematician, and in the early 1960s he did a calculation that would haunt him for the rest of his life. He calculated the cost of an Orion launch in human lives. Every nuclear explosion releases radioactive isotopes into the environment: strontium-90, cesium-137, and others. Unstable atoms that don't exist in nature, but are created in the heart of nuclear reactions. When you detonate a nuclear bomb in the atmosphere, these isotopes are lofted high into the air, where they spread around the globe. Eventually, they settle into soil and water. They enter the food chain. They accumulate in human bodies. And over time, they cause cancer. The horrifying thing about radioactive fallout is its statistical nature. You can't point to a specific person and say, "This fallout killed them." Instead, you increase the background cancer rate across the entire global population. Somewhere, someone gets leukemia who wouldn't have otherwise. Somewhere else, someone develops bone cancer. The victims are scattered randomly across the planet, dying years or decades after the exposure, never knowing what killed them. Dyson ran the numbers for an Orion launch. Each bomb detonated during the ascent would release a certain amount of radioactive material. That material would disperse globally. And based on the known cancer rates from radiation exposure, each Orion launch would statistically cause between 0.1 and 1 additional cancer death worldwide. Let that sink in. Every time you launched an Orion spacecraft, you would kill someone. Maybe not immediately, maybe not anyone you'd ever meet. But somewhere on Earth, your launch would sign someone's death warrant: a child in India, a farmer in Kansas, a fisherman in Japan. Random, invisible, inevitable. The team tried to rationalize it. In the late 1950s and early 1960s, the United States and Soviet Union were conducting hundreds of atmospheric nuclear tests, bombs far larger than Orion's propulsion charges, detonated purely for weapons development. Those tests were releasing vastly more fallout than Orion ever would. Compared to the ongoing nuclear testing, a few Orion launches would be a drop in the bucket, and wasn't opening the solar system to human exploration worth a statistical fraction of a death? Wasn't the alternative, remaining trapped on Earth, all our eggs in one planetary basket, more dangerous in the long run? But there was another problem, one that had nothing to do with fallout and everything to do with weaponization. If Orion technology became operational, it could be used for more than exploration. The same pusher plate that could take a crew to Mars could also deliver nuclear weapons anywhere on Earth with pinpoint precision. An Orion spacecraft was, essentially, an ultimate weapons platform, immune to interception, capable of reaching any point on the globe, able to drop nuclear bombs from orbit or even from suborbital trajectories. The military implications were impossible to ignore. If the United States developed Orion, the Soviet Union would feel compelled to develop their own version. The arms race would extend into space in the most literal way possible. And the same technology that promised the stars also threatened to turn Earth's orbit into a nuclear battlefield. For Ted Taylor, the moral crisis became personal in the most visceral way. While his wife was in labor with one of their children, Taylor sat in the hospital waiting room, unable to focus on the impending birth. Instead, he compulsively drew circles on maps of Moscow, blast radius calculations for the nuclear weapons he'd designed earlier in his career. Concentric rings representing different levels of destruction, total vaporization in the center, fires and collapsed buildings in the middle ring, radiation sickness in the outer zones. This wasn't about Orion specifically. This was about Taylor confronting what he'd spent his career creating. He'd been so captivated by the technical elegance of nuclear weapons design, the physics challenges, the engineering solutions, the sheer intellectual satisfaction of making something so efficient and powerful. But sitting in that waiting room, waiting for new life to enter the world, he was calculating death. The same mind that could envision a spacecraft to the stars had also created weapons designed to incinerate cities. Years later, Taylor would confess, "We were captivated by technical sweetness. The whole thing had gone out of control." He was talking about the nuclear arms race, but the sentiment applied equally to Orion. The technology was seductive. The possibilities were intoxicating. But could you separate the dream from the nightmare? Could you build a nuclear spacecraft without also building a nuclear weapons platform? Despite his growing doubts, Taylor couldn't walk away. None of them could. The vision was too compelling. They convinced themselves that the fallout problem could be solved. Maybe by launching from orbit instead of from Earth's surface, using conventional rockets to get the Orion into space before starting the nuclear pulse drive. They argued that the weaponization concern was overblown, that international treaties could restrict military use while allowing peaceful exploration. But the political ground was shifting beneath their feet. Public awareness of nuclear fallout was growing. The atmospheric nuclear tests that had seemed routine in the 1950s were now generating protests and international condemnation. People were learning about strontium-90 accumulating in children's bones from contaminated milk. They were hearing about cancer clusters downwind from test sites. The romance of the atomic age was curdling into fear. And then, in 1963, everything changed. The United States and Soviet Union signed the Partial Nuclear Test Ban Treaty, which prohibited nuclear weapons tests in the atmosphere, in outer space, and underwater. Only underground testing would be permitted. The treaty was a triumph of diplomacy, a small step back from the brink of nuclear annihilation. But for Project Orion, it was a death sentence. You cannot launch an Orion spacecraft without detonating nuclear devices in the atmosphere. That's the fundamental concept. Even if you use conventional rockets to get into orbit first, you'd still be detonating nuclear bombs in space, which the treaty also prohibited. There were no loopholes, no exceptions for peaceful use. The treaty killed Orion as surely as if Congress had defunded it. The team fought to keep the project alive. They proposed modifications, alternative designs, ways to comply with the treaty while preserving the core concept. But the momentum was gone. NASA was focusing on the Apollo program and chemical rockets. The military lost interest once the atmospheric testing ban made Orion impractical. By 1965, Project Orion was officially canceled. Freeman Dyson returned to theoretical physics, though he would spend the rest of his long life thinking about Orion and what might have been. Ted Taylor eventually left weapons design entirely, haunted by what he'd created, and devoted himself to nuclear non-proliferation efforts. The team scattered, the designs were classified and filed away, and humanity continued its slow, expensive crawl into space using chemical rockets, the same basic technology we're still using today. Here's what we lost. In an alternate timeline where Orion was built, the 1970s might have seen permanent bases on the Moon and Mars. The 1980s could have brought mining operations in the asteroid belt and research stations orbiting Jupiter. By the 21st century, we might have had self-sustaining colonies throughout the solar system and probes on their way to other stars. Instead, we've sent a handful of people to the Moon and never gone back. We've launched robots to explore the planets, marvels of engineering, but limited by the payloads chemical rockets can carry. We've built a space station in low Earth orbit, barely 250 miles up, and called it the pinnacle of international cooperation. The performance gap is staggering. The most powerful rocket flying today, SpaceX's Starship, aims to lift about 100 to 150 tons to low Earth orbit. Impressive, but still less than what a single Orion could have carried 60 years ago. And Starship uses the same fundamental technology as the Saturn V: chemical combustion, staged rockets, enormous fuel tanks. We've optimized the design, made it reusable, brought down costs. But we're still operating within the same basic constraints that limited the Apollo program. Orion would have shattered those constraints. It would have made space travel routine, almost mundane. Instead of sending a handful of astronauts on carefully planned missions, we could have sent entire expeditions with the equipment and supplies for extended stays. Instead of choosing between science and human exploration, we could have done both simultaneously on a scale that's still impossible today. But the cost would have been real. Those cancer deaths from fallout weren't hypothetical. They would have been actual human beings, dying from radiation exposure, scattered across the globe. How many deaths is Mars worth? How many for Jupiter? How many for the stars? These aren't abstract questions. They're moral calculations with real consequences. And the weaponization concern wasn't paranoia. Orion technology could absolutely have been used for military purposes. In a world where both superpowers had nuclear pulse spacecraft, the Cold War might have turned even colder, or it might have gone hot in ways we can barely imagine. The treaty that killed Orion also helped prevent the militarization of space. That's not nothing. So, was canceling Project Orion the right decision? That's the question that haunts this story. We sacrificed an incredible opportunity, perhaps the best chance we've ever had to become a truly spacefaring civilization. But we did it to prevent radioactive contamination and to pull back from the nuclear brink. We chose the precautionary principle over the pioneer spirit. We chose the people who would die from fallout over the future generations who might have grown up on Mars. There's no clear answer. Maybe both decisions were right. Maybe both were wrong. What's certain is that we made a choice, and we've been living with the consequences for 70 years. Today there's renewed interest in nuclear propulsion for spacecraft, but the focus is on nuclear reactors, not bombs. NASA is developing nuclear thermal rockets that heat propellant using a reactor instead of chemical combustion. These designs are safer, more politically acceptable, and don't require detonating weapons in space. But they're also far less powerful than Orion would have been. We're still thinking incrementally, still constrained by our fear of the atom's power. Project Orion remains the road not taken, the future we glimpsed and then turned away from. The hardware is gone. The team has passed into history. But the basic physics hasn't changed. Nuclear pulse propulsion still works, at least on paper. The bombs still contain millions of times more energy than chemical fuel. The dream of riding atomic fire to the stars is still technically possible. We just have to decide if we're willing to pay the price. And 70 years after Freeman Dyson calculated the cost in human lives, we still haven't answered that question. We're still trapped in low Earth orbit, still using chemical rockets, still dreaming of the stars but unwilling to grasp them. Project Orion proved we could reach the cosmos if we dared. But daring, it turns out, was the one thing we couldn't sustain. The story of Project Orion is ultimately a tragedy, not of technical failure, but of technical success colliding with moral reality. The spacecraft worked, the physics were sound, the vision was magnificent, but the cost was too high, or we believed it was too high, or we couldn't separate the dream from the nightmare. And so, we abandoned our best shot at the stars and condemned ourselves to crawl through space instead of soaring. Whether that was wisdom or cowardice, salvation or surrender, remains an open question. but the stars are still there, still waiting, just as unreachable today as they were when Project Orion died in 1965. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.